Hello everyone, my name is Santiago and I am very glad to present you our recent work about audio classification of the content of food containers and drinking glasses, along with Alessio Sompero and Andrea Cavallaro. Let's imagine a robot interacting with a person, and the person is manipulating an object before handing it over to the robot. We are then expecting the robot to reason about the physical properties of the object, for example, when only audio is available. These are examples of what the robot will hear. Our objective is to estimate the type of content and its amount within the container. This will help a robot applying the right amount of force when grasping the object. However, the containers vary in shape, size, and material. People manipulate objects in different ways and speeds, and at different distances from the robot. All of this affects the sound generated by the contact of the content with the container and makes the estimation challenging, in addition to room reverberations and background noise. Literature tackled the problem through both regression and classification, but none of the existing methods consider the manipulation of the containers or generalize the problem beyond the pouring of liquids in containers on a table. To solve the task, we present ACC, a model that consists of 3 convolutional neural networks and that decomposes the problem into 2 steps. First, it recognizes the type of action through an action classifier, and then classifies the content type and level with an action-specific classifier. Let's see an example. ACC recognizes the pouring action with the first classifier and thus selects the pouring model, which then classifies the type and level of content. Let's look at another example. In this case, ACC recognizes the shaking action, selects the shaking model, and again classifies the content type and level. Note that the action classifier has a third class, unknown, to recognize recordings with no action or with an empty container. Therefore, we map this action prediction to the empty container for this work. The modeling of ACC is based on Kurzweil containers manipulation, the only publicly available audiovisual dataset with people manipulating containers. The dataset features actions with 15 different containers, handling 3 types of content, pasta, rice, and water, at 3 different filling levels, empty, 50, and 90%. However, the dataset is unbalanced between the number of pouring and shaking recordings, and is recorded in the same room setup, but with the presence of different background noises across recordings. We also collected a number of additional recordings with the same type and amount of content and similar containers, but in another room with different acoustics and sensor to evaluate the generalization of ACC. The combination of the different filling types and levels result in 7 possible classes to avoid inconsistent or incompatible predictions. Before providing the spectrogram as input to ACC, we process the audio by downsampling the signal, normalizing the amplitude, and identifying the approximate beginning of the action with onset detection. We also temporally segment the action with a fixed window of 10 seconds to cover, on average, short and long actions. To train ACC, we randomly split the train set of Kurzweil containers manipulation into training and validation, and we then train each classifier independently. For the action model, we annotated the action performed and we trained with all training samples, while we only use the recordings annotated as pouring or shaking for the corresponding models, and the labels for filling type and level. As performance measure, we compute the weighted average F1 score to handle class unbalanced data. We compared the performance of ACC with 3 machine learning classifiers and 4 deep learning models that perform direct classification, and with 2 approaches that perform independent filling type and level estimation. Note that the first method also uses video. ACC has an architecture like VGG, but with 3 times less parameters. Looking at the scores for each data split and dataset, ACC achieves the best and second best score in the private and public test splits of CCM and the best score in the second setup. ACC outperforms all direct classification methods, while generalization is still limited for all methods, as we can see from the lower scores in the second setup. We analyze the confusion matrices of all methods performing direct classification. All methods tend to wrongly classify both levels, have full and full of the same type, while class empty is correctly classified by all models. However, ACC is a method that better classifies the filling type and level along the diagonal. Also, we analyze the confusion matrix of ACC's action classifier. The classifier correctly identifies all the actions, but remember that it associates the action unknown to the content class empty, based on the dataset characteristics. In this talk, we presented the first work investigating the recognition of the content and its amount in an unknown container that is manipulated by a person using only audio data. We designed a novel model, ACC, that decomposes the problem into two stages. First, identifies the type of action performed, and based on this prediction, selects a task-specific classifier for content estimation. As future work, we will improve the generalization to other setups and environments, and will investigate the complementarity with vision for addressing ambiguous cases, inaccurate estimations, or the unknown action.